Welcome friends. In this session, we will discuss about the current distribution in delta star transformer. We have started with the transformer protection in our last session where we have studied about the phase shift in a star delta transformer, how to determine the phase shift between the primary winding and the secondary winding in a star delta transformer or a delta star transformer. We have also discussed in that session how to draw the connection of YND11 or DYN1, YND1, and if a connection is given and due to some wiring issue or due to some external connection issues, if there is a difference in phase shift between the actual connection, like if the actual connection is YND1, but due to the external connection mismatch, the connection might change from YND1 to YND5, and how this can be determined. This everything we have discussed in our first session on this transformer protection series. And if you have any doubt regarding that, you can just go to playlist and watch that session, and as per your convenience you can see the particular section whichever is required for the understanding of the concept. Now, in this session, we will discuss about the current distribution in a star delta transformer for two different cases, and these two different cases are: first, the phase to ground fault on star side, and second, your phase to phase fault on star side. How the currents are distributed in a delta winding on after a fault on a star side, phase to ground fault, and a star side phase to phase fault, how the currents are distributed in the delta winding, that we will discuss in this session. Remember, we will discuss about the current distribution in 2-winding transformer, 3-winding transformer and auto transformer in subsequent lectures. We have already covered the phase shift in star delta transformer in our first session. So in case of any doubt, just refer that first session and you will definitely learn about this phase shift calculation. Now, why this current distribution in a star delta transformer is required to be understood is, again, the reason is same. We have to understand these concepts of current distribution and phase shift to understand the important transformer protection, like the implementation of differential protection using numerical IEDs. So in case you want to apply differential protection on a transformer using numerical IEDs, or you want to apply REF protection or backup overcurrent earth fault protection, for any types of protection you want to apply using numerical IEDs, you must have an idea of the current distribution in a star delta transformer. And remember, we are focusing on a star delta transformer in this session, and if you understand the current distribution in the star delta transformer, then it will be very easy to understand the current distribution in auto transformer and current distribution in a 3-winding transformer. In case of auto transformer, we will discuss about the current distribution in auto transformer with tertiary delta. So we will discuss with tertiary delta winding, and this tertiary delta winding will be applicable for 3-winding transformer also. And we will discuss when the tertiary winding is loaded and also the case when tertiary winding is unloaded. So we will discuss about each of these things in subsequent lecture. In today's session, we will focus ourselves only up to the current distribution in star delta transformer for these two cases: the phase to ground fault on delta side, star side, and phase to phase fault on star side. Apart from these two concepts, that is the phase shift in star delta transformer and current distribution, the another important thing is your CT star points. You must have heard several times that the CT star points are always formed towards protected object side, and towards protected object side, and we will discuss in our subsequent lectures that why these CTA star points are always formed towards protected object side. What happens if the CTA star point polarity is reversed? So you must have learned, or you must have heard several times during your commissioning work or testing work, that if this star point is reversed, then there is a chances of maloperation of differential and REF protection. But we will learn how this star point impacts our actual operation of differential protection. So we will cover these star points and then the auto transformer in our subsequent lectures. Today we are focusing only on star delta transformer. So let us begin with our topic without wasting further time. So now first of all, before starting with our topic on current distribution, remember the concept of current distribution is very easy if you can remember these fundamental concepts of transformer or any magnetic circuit: MMF balance equation or MMF balance rule. Basically, it is called MMF balance rule. This MMF balance rule is also called as ampere turns balance rule. Ampere turn balance rule. So now what does this ampere turn balance rule means? If you have two windings or two coils, suppose this is one coil and this is the second. Now in case suppose the current flowing through this is I1 with number of turns N1 and the current flowing through this is I2 and number of turns is N2, then in case of your transformer, this I1 N1 is always equals to I2 N2, and this is called ampere turn balance. I is ampere and N is number of turns, I2 and 2. So we will use this concept of ampere turn balance for our current distribution calculation, and for simplicity what we are assuming here is that for our case of current distribution in star delta transformer, which we are covering in today's session, current distribution in star delta transformer, our simple assumption is, one assumption is that the number of turns of primary is equals to number of turns of secondary, or N1 is to N2 is 1:1, and this is only for simplicity, only for understanding of our concept, because you know that in actual condition this will never be equal to 1:1 for normal power transformer. So now for simple understanding of our concepts, we are assuming this N1 is to N2 is equals to 1:1, and what it will make is that then your I1 into 1 is equals to I2 into 1. That means I1 must always be equal to I2, and we will use this concept, this simple equation for our current distribution in a star delta transformer. So now let us first draw a simple star delta transformer. So this is your suppose delta winding, and I am not going to discuss which kind of transformer it is, whether it is YND1 or YND11, that you can easily determine. And if you have any doubt, just refer our first session. And this is your star winding. So this is your star winding. Suppose this is a star winding which is grounded, and these are your three terminals on delta side, which is your suppose A, B and C. Similarly, in the star side, suppose the three windings or three phases are A, B and C. Now consider the first case. The first simple case is, this is the case 1, and in this case what we are going to discuss is phase to ground fault on a star side. Phase to ground fault on a star side. Now suppose there is a fault between C phase to ground. So this is a fault on a star side, phase to ground fault. Now if there is a fault between C phase to ground, so there will be a current flow like this. Suppose this is your current flowing in this winding, and suppose the magnitude of this current is 1 pu. Now because of our assumption of 1:1 turns ratio, that is this turns ratio is 1:1. So what happens is, because of this 1 ampere current, the corresponding 1 ampere current will flow in this winding also. So I is equals to 1 pu over here also. Now the second assumption that we are making here is, this is our second assumption now, we are assuming that load current is negligible for our analysis. Load current is negligible only for our analysis purpose. Load current is negligible for our analysis purpose. Now, what does this makes is that if load current is 0 or close to 0, that that is our assumption. That means the current in this winding is 0, current in this winding is 0. So, if current in this winding is 0, that means the ampere turns, that is 0 into 1 is 0. So, the corresponding here is also 0 and this is also 0. Now, our main analysis starts. This is the start side. In this side, there is a fault between C phase to ground. We want to determine what will be the current distribution inside or on delta side. Now, suppose because of this 1 pu current in C phase, the 1 pu current will flow through this winding here. Now, how we can get 1 pu current over here? We can get 1 pu current in this winding through this phase only, because there is this winding, there is 0 ampere turn is 0. That means this you can assume as open circuit. This is also open circuit. So now current cannot come from this path. So current in this will be 0. Now current might come from this path from phase A, like this is like this, and this might force a current from suppose this side. But if phase A is forcing the current from this path, then the direction of these two currents will be reversed. So the only possibility is that C phase will force the current, and this is your current from this side. Now once there is a current forced from this C phase, this current, so then your this current now in this winding, this current can go either this way or this way, but current cannot go this side because this is open circuit. So the only path for this current is through this winding. Now this current will reach here, and here now this current will have two paths. It can go this side or it might go this side, but it cannot go this side because this is open circuit. So your current of 1 pu now will exit from phase A. So this is your 1. So 1. That means what you see here is that the phase to ground fault on a star side, that means the phase to ground fault on a star side, this phase to ground fault on a star side, this was phase to ground fault, what it creates is, it creates a phase to phase fault on delta side, phase to phase fault on delta side. So phase to ground fault on a star side creates phase to phase faults on delta sides, creates phase to phase fault on delta side. Or this is in simple terms, it is called that or it is stated that the delta side, the reflected current due to the phase to ground fault on a star side, the current is now reflected in two windings or two phases. Current is reflected in not two windings but two phases. And due to this, when we discuss about our differential protection, the compensation matrices for this star delta transformer are to be selected very judiciously, very carefully for a star delta transformer, and in that star delta also for YND 11 or YND 1, we have to select the compensation matrix as per the phase shift provided by the star delta winding connections, and also keeping in mind this phase to phase and phase to ground fault current reflection. This phase to ground fault on a star side, when it is reflected as phase to phase fault on delta side, then your implementation of overcurrent and earth fault protection will also becomes very difficult, and it is very tedious job that we will discuss surely during our sessions on transformer protection, when we discuss in details about the various transformer protections. In this session, since we are focusing only on the current distribution in a star delta transformer, and we have discussed this first case of phase to ground fault on a star side, now this is the second case The second case is now the phase-to-phase fault. This is case 2, which is phase-to-phase fault on a star side. Phase-to-phase fault on a star side. So now we will draw again a simple star delta winding or a star delta transformer. This is your star delta transformer. Okay, and this is your star side. This is a star side and this is your delta side. Now suppose there is a fault between phase A and phase B. So this is a fault between phase A and phase B. So there will be current flow like this. This is current in phase A. Suppose this is 1 pu current. Current in phase B. Suppose this is again 1 pu current. And since we are assuming load current as 0, so suppose this is 0. If this is 0, so 0 into n number of turns is equal to 0. So ampere turn balance required or MMF balance required over here is 0. Now because of this 1 pu, the ampere turn balance here required will be 1 pu, and similarly here also we will have 1 pu. Now we will discuss the current distribution by using the same concept that we have applied in our last case of phase to ground fault. So now in this winding we want to have 1 pu current. So how 1 pu current we can get over here is through this side only. So this force A phase will force a current of 1 pu, and this current will have two paths. It can go either through this winding or it can go through this path, but this current of 1 pu cannot go through this path because this is open circuit over here. So this current of 1 pu will go through this path. Now in this winding, so when this 1 pu current comes here, this will have two paths. It can go through this side or it can go this side, but this 1 pu cannot go this side, because if this 1 pu goes to this side, then 1 minus 1 will equal 0, and now ampere turn will not be balanced condition, because the ampere turns over here will be 0 and ampere turns over here will be 1, so it cannot balance. So this 1 pu current of this winding cannot go to this side, but it must exit from here. Now the case which is very important over here is how this 1 pu current in the second winding or in this B phase winding will come. So B phase cannot force current, because if this forces the current, so then the current will be in the opposite direction and the MMF balance will not hold true. So the only possibility is that C phase will push the current of 1 pu for ampere turn balance. So C phase will push the current, it will go like this, because now this 1 pu current cannot go from this side because it is open circuit. So this 1 pu current will go from this side. So now if you see at this node, what happens is that 1 pu current from this side and 1 pu current from this side, the total current available over here will be 2 pu, and this is very important concept. Then that is a phase to phase fault on a star side. A phase to phase fault on a star side. Phase to phase fault on a star side creates, what it creates is a it reflects as a three phase fault on delta side, three phase fault on delta side, and most importantly the current distribution is now 211. What is the meaning of 211? That in one of the phases the current will be 2 times as compared to other 2 phases, and this 211 current distribution is very important, and this again we will study while studying our concepts of differential protection of transformer and the compensation matrices. So basically in this session we have discussed about the current distribution in star delta transformer in case of phase to ground fault on star side. Also in case of phase to phase fault on star side, how the currents are reflected inside the delta winding. Now in the next session we will discuss about the current distribution in case of two winding transformer, current distribution in two winding transformer. Also we will discuss about the current distribution in three winding trafo or transformer, and most importantly the auto transformer. During our discussion on auto transformer, we will discuss about the current distribution in auto transformer with tertiary delta. And this tertiary delta is very, very important because the one concept which I am going to explain in this session only, because of its relevance, because of its importance for our coming session, is that the importance of tertiary delta or importance of delta winding. You might have heard or you might have learned somewhere that delta winding traps zero sequence current. Delta winding traps zero sequence current. Traps zero sequence current. And now we are going to discuss how delta winding traps zero sequence current in a very, very simple terms. You know that in case of any faults on a transmission system, in case of any unbalanced fault on transmission system, if there is any unbalanced fault, you will have three sequences of current and voltage, and these sequences are positive sequence, negative sequence, and zero sequence. What I am explaining right now is that delta winding traps zero sequence current. So we will focus only on zero sequence current. So we will focus only on this zero sequence current. And you know that what is the meaning of zero sequence is that three vectors of equal magnitude with no phase difference between them. So this is your zero sequence. Now we will discuss how delta winding traps zero sequence current in a very, very simple terms. So suppose this is your delta winding. This is your delta winding, and now we want to study how this delta winding traps zero sequence current. So now, in case of any unbalance in the system or in case of any fault, unsymmetrical fault in your system, suppose there are three sequence currents available to you, that is I positive, I negative, and I zero. Now when this current reaches up to this point, we are focusing now only on the zero sequence current. So now sorry. So now we are focusing only on this zero sequence current. So suppose this is your zero sequence current in this phase, this is zero sequence current in this phase, and this is the zero sequence current in this phase. Why I have shown everything in the same direction is because IA0 must be in same phase with IB0 and must be in same phase with IC0, and these all have equal magnitude. So now once this current reaches up to this point, this current will have two paths. This current can go either through this way or this current will go through this way. So first let us consider that this current now goes through this path. So this is your I0. Now once this I0 goes through this winding, at this node this I0 will have two paths. It can go through this direction or it can go through this direction. But now I0 cannot go in this direction. Why? Because if I0 goes in this direction, then what happens is that this IB0 and I0 or simply IA0 will now, this IA0 and IB0 will now doesn't have a phase sequence of 0 degree, but it will have a different phase sequence. So it violates the zero sequence current. That means this I0 which is flowing through this winding cannot go out, it must now travel through this path. So once it is traveling through this path, when it is at this point, this current will have now again two paths. It can go through this direction or it can go through this direction. But again, this cannot go through this direction, because if it goes through this direction, then again this identity will not hold true. So this current now I0 must flow through this winding. So now it is going through this path, and at this point it will have two directions. It can go through this way or through this way, but it cannot go this way because again this will have opposite phase relations and this identity will not hold good. So the current must flow through this path only. And now what you can see is that over here is that once a zero sequence current enters your delta winding, it will always keep on circulating between these windings only. It cannot go out, and this is called the trapped zero sequence current in case of delta winding. Trapped zero sequence current, or also it is called as the trapping of zero sequence current, or this is called that zero sequence current flows through delta winding only, flows inside the delta winding, and it cannot go out. So this is very important for us when we discuss about the current distribution in auto transformer, current distribution in two winding transformers, and then current distribution in three winding transformer with tertiary delta. At that point of time, this concept of the trapped zero sequence current in case of delta winding is very frequently used, and it will be very important for us to utilize this concept, because suppose now this is your delta winding, this is a very simple delta winding concept. So suppose this is your delta winding. Now what happens is that once your zero sequence current comes inside, then the zero sequence current will keep on flowing like this, and this is your zero sequence current. So zero sequence current will always keep on flowing inside this delta winding, and this is called trapped zero sequence current, trapping or trapped zero sequence current inside of delta winding. And we will discuss in details about this in coming session. So we will keep up to this point only in this session. If you like the video, then do share it with your friends and other protection engineers, so that more and more people will understand these concepts and more people will get benefited through the use of these concepts in their industry, in their field. If you doesn't like the content, then also please comment in the comment section, so that we can improve upon in our coming sessions, and we can improve in the quality or the delivery of the lectures in the coming session. So we will keep up to this point only again. Thanks for watching. Please stay tuned for more such videos in future. Thank you.